All right. Well, thanks everyone for attending. This session that we're doing today is going to be complicated. It's going to be real complicated because we added a new feature into the Connexus Integrated Safety Suite, and I need to explain what it does, how it does what it does, why it does what it does, how it does it, and so on. And basically, if I could start real easy, the entire concept that we're shooting for here is comparison diagnostics, specifically external comparison diagnostics. So if I'm trying to measure pressure, I've got a pressure measurement going into the SIS. I've got a pressure measurement going into the basic process control system. I know that if I set a 2, 3, 5, 10% deviation alarm, that I'm going to get some benefit from that. I know that if one of those devices is stuck in place and the other one is still moving, I'm going to get a deviation. That's going to tell me that I have a failure. And when I have a failure, I can go repair things. So the ability to do those comparison diagnostics is something that previously we didn't include in our Vertigo software because, well, in a modern transmitter, the standard diagnostics, the internal, not the external, but the internal diagnostics inside the transmitter are going to be better than that comparison. And doing that comparison will actually not buy you anything if you're using new modern transmitters. That's why we didn't have it originally, but we do have it now because there are some devices where the diagnostics are not that great and you're going to want to supplement it. So let me share my screen, and I am going to be jumping all around, all over the place. I've got PowerPoint slides. I'm going to be opening up the standards. I'm going to be doing a lot of things. So let me start out in my web browser. Many of you are familiar with this. This is the single sign-on page for the Connexus Integrated Safety Suite. So I'm going to sign in using single sign-on. I'm already logged into Office 365, so it knows that, and it just lets me in. And I'm going to go, as I normally do, to General Oil and Gas Operating Company, which is that fictitious company that we created to do training classes and software demos. I'm going to go into the Texas City gas plant, and I'm going to bring up my safety instrumented function list. Now, all of this has been available for over a decade now. A lot of you are using this software. And when I drill down in, you'll see that, okay, a safety instrumented function is going to be built on sensors, logic solvers, and final elements. And then if I drill down into the sensor, you're going to see all of the attributes of the probability of failure on demand and the spurious trip rate calculations. And we do everything that we can to tailor our calculations to be consistent with the ISA 84.02 technical report for doing SIL verification calculations, and also the EC50, EC52, EC54 training classes. So we're doing our best to maximize the consistency to make things easy to use. Now, those of you that have taken the training class, and I'll show you some of the snippets out of the training class, know that there is probability of failure on demand is built of multiple components. There is the DU term for dangerous undetected failures. There is going to be a common cause failure term. If you have redundancy, what is the probability that multiple components fail at the same time for the same reason? And then there is going to be the DD term, or at least we have to handle dangerous detected failures. Now, they may result in an unavailability, as they do here, because I did not check trip on detected failure. which means when a failure of this component of this pressure transmitter occurs, I'm going to get an alarm saying that the device is in the failed state, but I'm not going to shut down the plant. I'm going to send somebody out the field to go fix it while the plant is online and running. Now, while I'm doing that, I'm supposed to have compensating measures that replace the safety instrumented function. But for the time period where between when the failure occurs and when it's repaired, I am unavailable, this component is unavailable, therefore the safety instrumented function is unavailable. That's why you see a PFD. Now, your other option, if I click here, is to trip on detected failure. Well, what that means is that when I diagnose that this pressure transmitter has failed, I'm just going to activate the SIF, have the valve move to the closed position, and shut down the plant. There, we did a conversion. We took that rate, and instead of it being an unavailability because I didn't shut down, we're going to convert it to a spurious trip because I did cause the plant to shut down, which is why there you'll see that spurious trip rate contribution for that failure rate as opposed to the PFD contribution. The other term that you'll see in ISA is online testing, where if I check online testing and I say, okay, I'm going to do an online test, it's going to take 4 hours. While I'm performing that test, I am unavailable to perform my safety function. There's the PFD associated with it. And then you'll see we also have the imperfect testing term down here at the bottom. Now, what is new? And if you took the EC50 class, what did we not show you? And that's this new external comparison. So let me uncheck some of these things. This external comparison is a new feature because what we're allowing you to do is we're allowing you to handle diagnostics that are done internally by the sensor, and we're allowing you to employ diagnostics by comparison externally of multiple different devices. So whether that's a 2 out of 3 vote where you're comparing the 3 transmitters, or you're comparing your basic process control system to your SIS. Now, in the training class for ISA, we didn't treat them separately because, in a 1-week training class, we need to keep things relatively simplified. But ultimately, these are different types of tests, and these different types of tests might need to be performed at different intervals, and the response to these might be different. So you'll see that for this external comparison, all right, let me step back a little bit. You'll see that trip on detected failure, you can decide whether that's going to be a spurious trip because you caused the plant to trip, or it becomes a probability of failure on demand if you choose not to trip the plant upon diagnostics. For external comparison, you only have the option of it being an unavailability. So what we're assuming in our calculations is that if you compare the BPCS signal against the SIS signal and you get a deviation alarm, that you're never going to trip the plant out there. It's going to be an unavailability. And now where things are going to get a little bit wonky is if you have internal diagnostics that will trip the plant, but your external diagnostics don't trip the plant, well, some of the diagnostics become a PFD, whereas another portion of the diagnostics might become a spurious trip rate. So we're necessarily splitting the diagnostics, putting them into different buckets and treating them differently because that's what's actually happening in the plant. So this use of external comparison, you really need to know what you're doing and how you're configuring your SIS and how you're implementing this, or you could end up with a very wrong answer. So my first warning is, if you haven't taken this training that I'm giving you right now in this webinar and truly understand what you're doing with the external comparison, just don't use it. Just rely on the diagnostics that are the internal diagnostics that are built into the transmitter. Okay, now with this external comparison, you'll see you could turn it on or you could turn it off. If you turn it off, obviously it's going to be a PFD contribution of 0 because, well, there are no external diagnostics. But if you are going to use it, you're going to need to know this comparison diagnostic coverage, which I'm putting at 99% right now, and the comparison interval, which I'm going to put at 0. And we'll come back to why these numbers are what they are in just a second. Question from David.
Hey, so on that external comparison, so are you assuming with that external comparison that there's a manual intervention, from an operator, or is this accounting for automatic, interaction? Like, I don't know, somehow you had some type of alarm or trip or something that's associated with that trip, or not trip, but some sort of action associated with it.
No, it's assuming that there's going to be an action associated with it. I'm sorry, a manual response to it. So the action will be a manual response for the technician, the operator, to tell the technician to go out in the field and fix it. So nothing is happening automatically. I'm not going to shut down based on this diagnostic, because that's consistent with what we see in industry. If you get a deviation alarm between your BPCS and your SIS, nobody is shutting their plant down based on that. So that's always going to make it an unavailability as to a spurious trip. But now let's talk about the numbers. And before I'm going to tell you what numbers we need to know. Then I'm going to go back into some training classes to explain where these numbers come from and why they are what they are, and why I don't recommend going past 90%, even though we give you the ability to do so. Okay, let me close down out of here, and I am now going to go into my PowerPoint slides, and I'm going to go into a Connexus training class. So this is the SIL verification training class that is in the Connexus Integrated Safety Suite in our Process Safety Training Center. Again, we're not here to compete with ISA. I highly recommend ISA. As a matter of fact, I'm teaching EC50 again. The virtual course starting on Monday. I highly recommend that as a vendor-neutral generic source of information on SIL verification calculations. But we have additional information in KISS that is more specifically geared to people who are using our software. Okay, so all of this is related to diagnostics. So what is a diagnostic? At the end of the day, a diagnostic is a test, but the difference between the manual proof test that you do once every 5 years and a diagnostic is that the diagnostics are generally being done at a very high frequency in comparison to the manual proof test, and they are generally being done automatically by the equipment and not through a manual test. So periodic component testing, we're going to detect the failure. And again, it's typically automatic online and more frequent than the overall test interval. Now, why do we do diagnostics? Well, number one, if we detect that a failure is present, we can just shut down the plant. And what you did there was you took a dangerous failure and converted it to a safe failure because, well, you shut your plant down. You're not going to continue to operate in the presence of a component that we know is in the failed state. So the big benefits of doing your diagnostics is that you get online fault detection. So while the plant's up and running, you're detecting failures instead of waiting until a turnaround. You're going to be able to repair faster. So if your test interval is 5 years and a component fails, on average, it'll fail halfway through. So that means your device will be in the failed state for, on average, 2.5 years before you know about it and have the capability to repair it. Whereas if we're doing high frequency online diagnostics, you can repair your device within 8, 24, 72 hours of that failure actually occurring. So you're getting a shorter mean downtime and a lower unavailability. That's why we do diagnostics. It improves our PFD and it can improve it dramatically. Now, let's drill down a little bit into what do we mean by diagnostics. Actually, I should have put that in. Oh, trouble there. There we go. I should have been in this mode the whole time. Okay, so what do we mean by diagnostics? We are talking about specific tests. And when you buy a transmitter that has a diagnostic coverage of 95% or whatever they do, it's not just one test that's being performed, it's an entire arsenal of tests that we're going to be performing. So what do these tests look like? Well, there are reference diagnostics. So I know that my milliamp signal should be between 4 milliamps and 20 milliamps. And if I'm off scale low or off scale high, that means that the device is in the failed state. You might take your output signal, feed it back to an input, and make sure that the signal you're getting out is what you actually expect. That's a way that you would confirm the operation of a D to A, digital to analog converter. You might get an improper response to a command. So you can pulse a signal in, watch the signal come out, and if it doesn't match what you expected, then there's going to be some sort of failure. So those are reference diagnostics where we're comparing the signal we have to a reference. Then there's comparison diagnostics, which is what we're talking about here, where you have multiple channels and you're comparing their signals. Now, what we're discussing in this attribute of the Vertigo software is an external comparison, but you can also do an internal comparison. So your pressure transmitter very well could have two A to D converters, converting that analog measurement to a digital measurement, and then it compares those two measurements to make sure that they're the same. All that's happening at a high frequency inside the transmitter itself. And then there are things like program sequence monitoring, like your watchdog timer. And down here at the very bottom, I say built-in versus custom developed, especially when you're talking about things that are in your SIS logic solver. But the more formal term that is used in the 61508 standard is going to be built-in diagnostics. Well, built-in are called internal diagnostics, and then the bolt-on or the custom developed are going to be called external diagnostics. So is it the subsystem itself that's performing the test? That's internal. Or is there additional equipment that's testing the subsystem? That would be an external. So now when we're using the DCS to compare a BPCS transmitter and an SIS transmitter, that's going to be an external diagnostic. It's an external diagnostic of the form comparison. That's going to be important when we start talking about how much credit do we give this diagnostic? And that's going to be important for our discussion because that's a number that you are going to need to type in to the Vertigo software. Okay, so those are how diagnostics are performed. I'm going to kind of skim through some of these slides now. Here we have definitions of diagnostic coverage, which is what is the frequency that can be detected divided by the total frequency. And then I kind of go and show you how you're going to break your failure. You're going to continue to break your failure rate down based on that CA, automatic diagnostic coverage. And as you know, if you've taken a course with me, sometimes you're going to get your failure rates in this representation. Sometimes you're going to get them in this representation. It's very easy to switch back and forth between those two representations. Right now in Vertigo, we're using this representation with total failure rate, percent safe, diagnostic coverage is safe and dangerous. So kind of looking at a typical piece of information that you get in a third-party FMEDA of a safety instrumented system component, it might tell you that there's a certain failure rate where you fail high, there's a certain failure rate where you fail low, there's a certain failure rate where you fail low because of diagnostics, and then there's fail dangerous undetected. So when the equipment vendors are going through that process of determining what my diagnostic coverage is, they basically go one failure mode at a time. So for this failure mode, what is its failure rate? And then what diagnostic am I going to use to try to detect that failure mode? What test? So fail high is detected by the test, the reference diagnostic test of, is the signal over 20 milliamps? Fail low, both of the fail lows will be detected by the diagnostic test of the reference signal. The signal is less than a 4 milliamp reference. So all these are reference diagnostics, not comparison diagnostics. And then finally, dangerous undetected. I have no diagnostic that's going to be able to detect those. That's why it's called dangerous undetected. So looking at that thought process in a failure modes and effect, FMEDA, failure modes, effects, and diagnostics analysis. Again, we list out all of our failure modes, we list out the failure rate, and then we assign that failure rate to being either safe or dangerous. Then we'll list off yes or no. Is it detected? If it is detected, what test am I using to make that detection? And if it is detected, then your failure rate is going to carry over into the appropriate column, either covered or not covered, safe. And then that's how we calculate these numbers on what the diagnostic coverage is. Okay, so that's diagnostics. Let me close out of here. And so that's what diagnostics are, and kind of the difference between a comparison diagnostic and a comparison diagnostic and a reference diagnostic. Actually, before I leave this, let me bring this back up. Now, here's the rub. So right now, I'm saying that my transmitter has a 69% diagnostic coverage of just using its internal diagnostics. Well, what would happen? How would this number change if I used a comparison? And I used a comparison between my SIS transmitter and the BPCS transmitter. Okay, now things are going to get really hairy and really confusing, because let's say that my comparison is 90%. So and this is going to be the next topic. How good are the comparison diagnostics? Okay, so let's say my comparison, which is I'm just going to compare the two transmitters and do a deviation alarm. Let's say that that is capable of diagnosing 90% of failures. And that's a number that we're going to use. I'm going to recommend that you use, but only under certain very special circumstances. So what do I do in my calculations? Do I say that, well, okay, my internal diagnostics detected 69%, and now my comparison diagnostics are going to be able to detect 90% of what's left? So if that were the case, and now I need to bust out my calculator. So if my bring up my RPN 48 calculator here. So if I can detect 69%, that means that 31% of my failures were not detected. If I multiply 31% by 0.9, so 0.9 times, that's 27.9%. And then if I add my 69% back in, now I'm all the way up at 96.9% if I consider both. Is that correct? Should I be doing that? Is that valid? No, it's not valid. Squish this out of your mind. That is the incorrect way to do it. You cannot do this. This 90% is a total. It's a cap. It's not that we're detecting 90% of what the internal diagnostics didn't detect. Why? Because the comparison diagnostics and the internal diagnostics very well will both be able to detect the same failure mode, and they will both fail to detect the same failure mode. So let's look at this fail high. So if one of my two transmitters fails off scale high, then the internal diagnostics are going to see that the milliamp signal is greater than 20 milliamps and fire off the diagnostic signal saying that the transmitter is in the failed state. Well, your comparison, your deviation alarm is also going to fire off, telling you that your comparison also detected that same failure mode. So when we put this number in, so the diagnostic coverage of the external comparison, we are not going to assume that that is above and beyond what the internal diagnostics did. We are going to set it as a limit. So instead of 90% of the 31% remaining, basically 90% becomes your cap. So if your internal diagnostics, instead of 69% or 95%, then this external comparison bought you absolutely nothing. And the diagnostic coverage is going to be 95%. And the comparison literally buys you nothing. But if your internal coverage is the low 69%, or you have no diagnostics, then the coverage is going to be, and it's going to max out at whatever you say this coverage is. So let's take a look at how this is going to be implemented in the software. Let me get the item back out. And what I'm going to do now is I'm going to go and I'm going to just create a new sensor type. And I'm just going to call this EDS new demo sensor. And I'm going to give it a failure rate of 1E minus 6, just to make my math a little bit easier. Actually, I'm going to give it a failure rate of 2E minus 6 and a percent safe of 1. And I'm sorry, not 1, 50 is what I want there. So 50% safe, which means our lambda S is 1e minus 6 and our lambda D is 1e minus 6. And I'm going to start off by putting my diagnostic coverages at 0%. No data reference, no database revision. I'm going to leave this at architectural constraint type A. Insert this. And then I'm going to play around with one of these safety instrumented functions. So I'm going to go to this safety instrumented function. I'm going to mess it up. I'm going to add a new sensor that's going to be based on Ed's new demo sensor. And I'm going to call this pressure transmitter 777. Okay. Just put in a test interval so that we have something. I'm going to go with 1 out of 1 voting. Sorry. Bear with me. Actually, I should leave that there. Okay, I'm not going to put any process connections in or anything. Okay, so what you'll see is right now, based on the information that I put in, my lambda DU got calculated out to 1e minus 6, and my lambda SU got calculated out to 1e minus 6. What I'm going to do now is I'm going to say, okay, this transmitter has no diagnostics, so I'm going to put in an external comparison, and I'm going to say that I get a 90% diagnostic coverage. And this comparison interval, if you go back, and I'll show you the equations out of the ISA training class here in just a second. The dangerous detected failures are an unavailability. That unavailability is based on the mean downtime. The mean downtime is a function of this mean repair time plus the amount of time that it takes to perform the test. So a comparison between signals is going to occur once a scan. So let's say a scan happens, twice per second, 500 milliseconds. Well, if I add 500 milliseconds to 72 hours, I still have 72 hours within your significant digits. So very high speed comparisons, we always put in a test interval of 0. And you'll see that it calculated this 6.8 E minus 5. And how it calculated the 6.8 E minus 5 is that it basically created a lambda DD for the external comparison that is going to be 0.9 times lambda D. Okay, and let me turn this off again and turn it on again. Now, what I'm going to ask you to do, so look at this number and remember 4.38 E minus 4. 4.38 E minus 4 is based on a lambda DU of 1 E minus 6. If I put this external comparison of 90% down, you'll see that my PFD here went down dramatically. It went down by an order of magnitude. Why? Because I decreased my lambda DU by an order of magnitude by converting those dangerous undetected failures into dangerous detected failures. Now, I'm not shutting down the plant, so I still have that 72-hour unavailability when a failure occurs, but that PFD contribution is small in comparison. So we've got ourselves not quite an order of magnitude improvement in the PFD. Now, try to remember this number of 6.48 E minus 5. I'm going to write that number down right now. So 6.48 E minus 5 is going to be the PFD contribution of 90% of the 90% of the dangerous failures. All right, let me cancel out of here. And what I'm going to do now is I'm going to go back and I'm going to update that sensor type. So I'm going to go back to Ed's new demo sensor, but now I'm going to say, well, this device has not 90% safe, but its internal built-in diagnostics are 90%. I'm going to hit update. And now I'm going to go back to that sensor that I was diddling with. Hopefully. Where is that guy? Was he here? I don't even remember which safety function I was messing around with. Let's assume it was this one. So I'm going to go ahead and I'm going to add a new sensor. So I'm going to, where is... You know what? I never saved PT777. So I'm going to go ahead and add new sensor again. And it's going to be Ed's new demo sensor. It's going to be PT777. And what do I need to give it? I need to give it a test interval. I need to give it a voting arrangement so that the calculation will run. Okay. So there we go. 4.38 E minus 4 is what our lambda du is now. If you remember previously, it was -3. So the calculations work out exactly the same way. The lambda dd, or I'm sorry, the lambda du here is exactly the same as it was before when I put in a 90% diagnostic coverage here. Now, in this case, you'll see that when I put in a 90% diagnostic coverage, the PFD contribution here is 0. Why? Because this external comparison bought me nothing, because my lambda DD already reflected a 90% diagnostic coverage of the internal diagnostics. So what I'm just showing here is any number up to 90% is not going to give you anything because you're already getting 90% from the internal diagnostics. Only when the external diagnostics give you more, and in this case, let's say we're going to go up to 95%. Now you see a little PFD contribution from the external comparison, and you'll see that the PFD contribution for dangerous undetected failures dropped again. So you kind of trying to boil it all down, the external comparison gives you a maximum that an external comparison will provide to you. It doesn't do that in addition. It won't go above and beyond the internal diagnostics, and it assumes that the internal diagnostics will detect pretty much exactly the same stuff that the external diagnostics will detect. If you've got a really good transmitter, then the external comparison won't buy you anything. But if you have kind of a generic transmitter that's only getting you a 60% coverage, then this external comparison is going to finally buy you something, because it's going to get you up to 90%. Not 90% of what's left, just up to 90%. Okay, so that kind of explains the details of how the diagnostics work, or how to incorporate them into your calculations, the fact that it's a limitation, a kind of an upper limit as opposed to something that works in addition to the internal diagnostics. So we kind of got all that lined out. Now, the big question you have to ask yourself, and you saw, is I was typing these numbers in. These numbers don't get built into the software. We're not going to guess for you. We're not going to put a number in for you. We're not going to limit what you do. We're going to allow you to put in 99.9%. We're going to allow you to put in 99%. We're going to allow you to put in 90%, whatever you want. You have to make the judgment. on what is appropriate. So now the next question that you have to ask yourself is, well, what number is appropriate for comparison diagnostics? Now, many of you have taken the ISA EC50 training class, which again, I will be teaching the virtual class starting on Monday. If you are interested, we will still accept a registration. In that training class, you'll see that when we were comparing two transmitters, we assumed 90%. And when we were comparing three transmitters in a 2 out of 3 vote, we assumed 99%. Well, it turns out that there's actually a basis for where those numbers came from. And that basis is not IEC 61511. IEC 61511 gives you no guidance on this, no help whatsoever, because this is kind of an equipment vendor in the weeds details. So when we're talking about equipment vendor in the weeds details, we need to drop 61511 and go back to the mothership, go back to the umbrella standard IEC 61508. So let's go ahead and take a look at what IEC 61508 says. And all right, let me, again, I'm kind of jumping around here. So, okay, so I'll kind of make a long story short, and I'll explain where all this stuff comes from in just a second. But IEC 61508 says in table A18 on page 56 of part 2, there's a table that says for sensors, these are the diagnostics that are commonly used. Failure detection by inline monitoring, analog signal monitoring, test patterns, input comparison, reference sensors, positive activated switches. And for all of these diagnostic techniques, what is the maximum diagnostic coverage considered achievable? Well, you'll notice it says, well, for this, it could be low or medium. For this, it could be low. For this, it's high. And we were talking about input comparison by voting redundancy. 61508 says that is high. Great. What the hell does high mean? Well, I'm glad you asked. Let's go ahead and pull up the ISA training again. So this is the ISA EC50 training. And there's a section in the EC50 training that talks about diagnostic coverages in the discussion of fault tolerance tables. So if you remember the fault tolerance tables in the, there we go. In the 1511 standard, the fault tolerance tables just say, well, what is your SIL? This is how much hardware fault tolerance you need. But if you go into 1508, it has different categories of safe failure fraction. Well, guess what, people? These categories are the numbers that the 61508 committee applied to the tables. This one here, 60% to 90% of the, so that 60 to 90% would effectively be a probability that the test will be successful. So 60 to 90%, this one is low. So let me get out my magic pencil. Actually, let me go into this mode. So 60 to 90%, the standards writer said this is a low diagnostic coverage. 90 to 99% is a medium diagnostic coverage. And greater than 99% is a high diagnostic coverage, where less than 60% is, well, we could call it very low. But basically, the 1508 standard says that if your diagnostic has a less than 60% chance of actually being able to diagnose the failure, we're not taking any credit for it at all. So it kind of goes away. All right. So in the parlance of IEC 61508, we have low diagnostic coverage, medium diagnostic coverage, and high diagnostic coverage. Those correlate to 60 to 90, 90 to 99, and greater than 99, respectively. So let's jump out of here and go back to the 61508 standard. And so basically what they're saying here, if I could turn on my magical pencil, is that analog signal monitoring over here, why will my magical pencil not work? Because that's the day that we're living in. All right, my magic pencil is not working, so I'll just have to point with the pointer. So analog signal monitoring low means that you should only expect, yeah, my pencil doesn't work, this to work 60 to 90% of the time, 60 to 90% diagnostic coverage. Test pattern. So what would a test pattern be? It's kind of shooting different signals in at different frequencies and reading the output and making sure they match. That's going to be a high diagnostic coverage. And then here we go. Input comparison, voting, 1 out of 2, 2 out of 3, or better redundancy. That has a high degree of diagnostic coverage. So, damn it. Anyway, I keep struggling trying to write on the screen, but the computer won't let me. That's greater than 99% is what the standard says. Now, are you going to get that in your plant? No. And let me tell you a whole bunch of freaking reasons why the answer is no. For this high diagnostic coverage, 99%, we're basically assuming that the 2 or 3 comparisons are occurring at the same level of quality using the same type of equipment. So if I did 2 A to D conversions inside the same transmitter and compared them, I would expect a high degree of diagnostic coverage, greater than 99%. But here, you're not doing that. You're getting one BPCS transmitter that's getting A to D in the DCS. You have another transmitter that's getting A to D in the SIS. So the quality of your measurements is not the same, and there could be a lot of discrepancy between the signals just based on the different components you have, the different maintenance activities, maintenance records that you have, and then the external stuff like signal conditioning, differences in locations, differences in elevations. There are a lot of things that can cause those two transmitters to read different signals other than a failure of the device. Now, the other note, this is the big bad boy. This is the one that's really important. This high diagnostic coverage is only valid. It's only valid if the data flow changes within the diagnostic test interval. Okay, I didn't mean to do that, but now we've got a little highlight at least. Only if data flow changes within the diagnostic test interval. So let me give you an example of where your external comparison is absolutely, unequivocally, completely worthless. Let's say I have a knockout drum upstream of a compressor. That knockout drum is always empty because we're in bone dry hydrogen service. So, we've been running for 10 years and there has never been a level in this vessel because no vapor ever comes into this pot. Then all of a sudden, something goes wrong upstream and I slug liquid into the inlet of the compressor. It goes into the knockout pot. What are the chances that that diagnostic is going to help you at all? It's not. I mean, it will only be able to tell you that that dangerous difference between the signals has occurred when that level starts to go up. So, and when the level starts to go up, you've got like a couple minutes before that liquid is in the compressor. You can't do anything about it. So that kind of shows you that, and let's kind of, drill down on that. Let's say that you've got an A, B, and C, or an A and B transmitter, and you're at 0, and the A transmitter gets stuck in place at 0. Well, you don't know that until the level fluctuates and the difference between A and B gets significant. Well, if that change only precedes your plant exploding by a few minutes, you've got no basis for taking any credit for it at all. So again, this is something that you need to look at. So what is Connexus's recommendation based on this? And before I give you my recommendation, I will say that the 1508 standard allows you to take up to 99%. We at Connexus do not recommend taking that degree of diagnostic coverage. So a little bit more detail on the 61508 standard. This is page 56. This is page 51. So you can, just for your edification, you might want to open up the 61508 standard and take a look at what it says about what the different types of diagnostics are available, because it gives you a full range. So again, here we go. There's if you didn't believe me before, low 60%. Medium 90%, high 99%. Table A1 is going to give you some of the qualitative attributes that the standards committee made in determining whether it's low, medium, or high. So, stuck at will be detected at low, and then DC faults and drift and oscillation. Drift and oscillation will only be detected at the different failure modes. So really good reading here. Table A1 just kind of gives you an overall feel for, what are the tests, how much credit can we take for them, and then when you get to the balance of the tables, now you start looking at specific pieces of equipment. So for electrical components, these are the failure modes in the left-hand column, or I'm sorry, the diagnostic techniques, and then the maximum coverage is available. So you do that for electronic components, electrical components, processing units, and then the one that we were looking at specifically was here in A13, which was related to sensors, and the specific test that we were looking for was input comparison, and the standard says high is possible, but only if and only if the data flow is going to change within the diagnostic test interval. And I would back out a little bit and say that the data flow needs to change within the process safety time, because I need to know that I'm going to be able to detect and repair before I get into trouble, or detect quick enough that I can take some sort of manual action to be able to get me to a safe state. Otherwise, what's the point? So, okay, so now All right, Dave, before I give you the final word on what our recommendation is, question.
So just speaking to that, what you were just saying right there about, within the process safety time. So you should probably consider like operator response to an alarm, like the 20 minutes type
Yep,
figure, because that's what's going to be happening.
absolutely. Absolutely. Excellent question. Okay, so here we go. The Connexus recommendation for the numbers that you put in, and did I shut out of, no, I've got Vertigo up still. So when you're going in and you're assigning a diagnostic, or when you're looking at a component, if you're doing an external comparison, first off, you need to look at your dangerous detected versus dangerous undetected. Specifically, you need to look at the diagnostic coverage that you're getting internally. If you're internally getting more than 90%, don't even bother wasting your time putting this external comparison here. So this external comparison is if your diagnostic coverage internal to your device is significantly less than 90%. If it's 90% or greater, don't even bother using external comparison. Now, if you're going to use external comparison, your comparison interval is going to be 0 because it's going to be done once every PLC or once every DCS scan. And that's generally going to be significantly more than your mean significantly more frequently, a much smaller period than your mean repair time. So it's, whether it's 500 milliseconds or 2 seconds, doesn't matter. Just make it a 0. And then your external comparison, we recommend that you limit yourself to 90%. Furthermore, we only recommend doing an external comparison, taking credit for an external comparison if your process moves. So your pressure is going to be varying over the normal state of operations. It's going to be varying. And how much does it need to vary? Well, that depends on what your deviation alarm is. So if you're trying to take credit for a 10% deviation alarm, your process variable should be regularly, more than once every 20 minutes or so, be varying more than 10%, which doesn't happen very often. If you're doing a 2% or a 5%, then you should be varying more than 2% or 5% respectively at a, we're going to kind of use a little bit of judgment, a little bit of sanity and gut feel to say, okay, well, once an hour, I'm going to want to see that kind of variation in the process signal, or once an hour is probably a good item to use. If you back off to like once a day, a whole lot less effective, because the question you're going to ask yourself is, how long can a component have failed in place and the measured variable not moved enough for you to diagnose that you're stuck in place? How much time on average is that going to be? So rule of thumb, I'm going to go with like an hour is probably a little bit more aggressive, but not completely unreasonable. If you wanted to be a little bit more conservative, you might want to back that off to like 20 minutes or so. But this external comparison really only effective if your process variable is moving. If it's not moving, then there's not a whole lot of justification for using it, i.e. the old level in a knockout drum that never has any level in it, your external comparison diagnostics are not going to be of a whole lot of value there. Okay, so with that, I have spent an hour talking about the concept of external comparison as a diagnostic coverage. And at this point in time, I am going to go ahead and open the floor to questions, beginning with Alberto. Alberto, what can I do for you?
Hi, I have a couple of doubts. One regarding the example that you have shown with the failure mode effect analysis. If you could please show this up.
Are
you hearing me properly?
Yeah. Sure. Bear with me for a second. So here, this is the failure modes and effects analysis.
Exactly. Here you are, this dangerous coverage is only taking into account the dangerous failures. So if we compare with this low, medium, or high coverage that you have shown in the ISC 61508, this would be a low
coverage of dangerous failures, correct.
Yes. But you have some way related this with the safe failure fraction. So we have to take into account for the estimation of this low, medium, or high, all of these 55 fits that we have for the, you know what I mean? I mean, this 69% is not taking into account it's only taking into account the 228 fits related to dangerous detected, but the 55 related to safe detected are not taken into account. So I mean that we have to add up, not to aggregate these numbers.
Well, right. I mean, so
you get my question.
Dangerous diagnostic coverage of 69% is the dangerous detected failure rate here divided by the total dangerous failure rate here. So 228 over 329. This coverage is not the same as the safe failure fraction. The safe failure fraction is going to be, let me erase these and kind of clean things up. It is going to be the safe failure rate plus the dangerous detected failure rate divided by the total failure rate. So 55 plus 228 over 384, that gives me a safe failure fraction of 74%.
Yes, I have no doubt with this. It was more related with the diagnostic. If we're talking about low, up to 60%, medium, between 60 and 90%. That coverage is the same as the dangerous coverage that you are showing here, this 69%. I guess it's not.
It is.
Okay. So you are not taking into account the safe failures.
No, because so in this case, the safe coverage is going to be 55 out of 55. So the safe coverage is very high. The dangerous coverage is low. The safe coverage is very high.
Okay. I was asking this because in one slide you have related with the safe, the low, medium, and high. You have related with the safe failure fraction. But okay, it's clear.
Right. That number... exactly. I was just showing where the numbers came from. And I was just trying to demonstrate that high, medium, and low are ranges that were defined by the 61508 committee of 60 to 90, 90 to 99, and greater than 99.
Okay.
Yep.
Okay. So, and the second doubt is in the example in your pressure transmitter, what you have only. I mean, there was only one sensor with a potential of 1 out of 1. That is possible to have a internal diagnostic with only one sensor, because in the table that you have shown from the IEC 61508, the input comparison is always talking about 1 out of 2, 2 out of 3, or better redundancy. You know what if you can show this table, I mean, in your example, you have only used one sensor, a rotation 1 out of 1. I mean, with
Right.
one sensor, you could have internal diagnostic. I guess yes, but I would like to confirm.
So I guess in terms of the diagnostics, so let me bear with me for a second. Let me get this guy up. So in terms of what the diagnostics are, the input comparison requires multiple channels to perform the diagnostic. These other diagnostic techniques do not require a separate transmitter.
Okay.
So a 1 out of 1 can do analog signal monitoring. A 1 out of 1 can do test pattern. A 1 out of 1 can do online monitoring. It can do reference sensor. A 1 out of 1 device can do all of those internally. And of course, then they are the internal diagnostics. This input comparison requires 2 A to D converters. Now, if you have 2 A to D converters inside a single transmitter, then you can do that as an internal diagnostic. But if you have 1 A to D converter in your PL or in your transmitter, and then you're going to compare that to an A to D from a different transmitter, then that would be an external diagnostic because the other transmitter is not internal to the device that you're looking at. So many of these diagnostics are possible for on an internal reference basis, but the comparison, while it can be done internally, what we are looking at is the ability in Vertigo for you to model it with an external transmitter. Now, you can use the number that we have. It is just a number. So if you're using 2 out of 3 transmitters or you're comparing 5 transmitters, we're not, the assessment of what external device you're using and how many external devices you're using is going to impact what this coverage is. So maybe if you had a 2 out of 3 vote, you might want to call it 99% instead of 90%. But we're not making that decision for you. In the software, you need to decide what coverage factor you're going to use and input it. And that coverage factor is a function of what, how many other devices that you are capable of making a comparison to. I don't know if that answered the question directly.
Yes, Ed. It's been perfectly clarified. Thank you very much.
Okay, very good. All right, Chris, were there any questions in the chat that I didn't get to?
Yes, Michael put a comment in here. So we can't use external comparison for instruments that have different spans. Commonly the case for, say, separator LIC and separate spanned LTs with alarms and trips for high and low level.
That gets a little bit difficult because a signal drift. So, all right. So you have to ask yourself, what failure modes are you trying to detect with this external comparison? And honestly, the external comparison is intended for 2 failure modes. One is going to be stuck in place, and the other one is going to be signal drift. Now, if a 1% change, or let me say a 1 foot change in level in your vessel if that means that one transmitter changes by 1 milliamp, but the other transmitter changes by 2 milliamps, it's not that you can't do a comparison of those, but your comparison got stupid complicated because you need to, in your the code that you write to compare the signals, you need to put in a factor that says this transmitter needs to be moving twice as fast as the other transmitter. So I'm not going to tell you that it's impossible to do it, but doing it is really complicated because you need to understand what a comparison between those two signals actually means in terms of whether or not you're stuck in place or whether or not you've drifted. Honestly, if you convert everything to engineering units, then the comparison of engineering units should take all those vagaries into account. But honestly, I haven't thought that through and done the math, so don't quote me on that as absolutely true. It feels like it would be true, but I would need to kind of crunch through the numbers and run some example cases to confirm that. But yeah, that's a good point. I mean, if 12 milliamps on transmitter A and 12 milliamps on transmitter B mean different things, it's really hard to make a comparison. All right, anything else on there, Chris?
I do not see anything else. Anyone want to bring anything up before we go?
I have one question. Instead of considering this as a comparison credit, I have a question. Like,
Yeah.
Instead of considering this as a comparison diagnostic credit, can I consider this as a partial proof test credit, like partial stroke test in the valve? We said every time we move, we can get some credit. Same way, like if my process parameter is varying every month, let's say 5% or 10%, and I have LRM at 2%, comparison diagnostic. So
very interesting question. And the answer is yes, absolutely, you can do that. So diagnostics are partial tests. And what we're doing with what we're doing here in this external comparison box, we have two fields. The first field is what percentage of the failures can it detect? And the second item is how often is this test performed? So if you are doing a partial stroke test on a valve that happens once a week, you might say that my coverage of that test was 70%, and I am going to perform that test once a week. So once a week is going to be 24 hours times 7. That's going to be 168 hours. And there you go. So if you want to put a little conservatism in there, you could put in the frequency at which the variables differ enough to actually be a valid test. That's actually, I had never thought of that because even though the comparison happens, once every 300 milliseconds, if the process variable doesn't move, you don't really have a test. But if you know that you're going to move it dramatically once a week or once a month, you could put that interval in as the comparison interval. So excellent question, because you gave me an answer to something that I hadn't come up with an answer for. Yeah, we could simply, instead of not taking any credit at all, we could simply change this comparison interval. And when you change this comparison interval, you're going to be increasing that unavailability, meaning when a dangerous detected failure happens, it takes a longer duration of time to know that you're in the failed state, and thus you can't repair until you know that you're in the failed state, which could take up to the duration of the test. So excellent question, because you helped me figure something out that I didn't have an answer to. I appreciate it. Okay, well, thank you everyone for your time. This is a very esoteric, this is PhD level SIL verification. So I appreciate you, and I thank you for hanging with me as we went through this process. Any questions at any time, always feel free to send me an email, and I'll be happy to answer it for you.
Thanks again, everyone. See you next month.